Okay, you ready for another one? I feel bad. I feel like this is might be feeling more difficult to you than it needs to be, at least the whole error part. So I'm hoping that when I get to the error in this one, part D, I can make it make a little bit more sense. But first, let's start A through C, which shouldn't be too problematic, just requires a little bit of thought and some explanation about what the heck this is talking about. So we start off with, let f of x equal this crazy function. The graph of y equals this. What the heck is that? So I wouldn't even know what they're talking about, but this is the absolute value of the fifth derivative of x, of f with respect to x. This is saying that this graph is representing the fifth derivative of f. So if I needed to find out a fifth derivative for some reason, I'd be able to use this graph to do so. So for right now, we can kind of ignore it because I have no need for it, at least right now. So here we go. Part A, write the first four non-zero terms of the Taylor series for sine about x equals 0, and write the first four non-zero terms of the Taylor series for sine of x squared about x equals 0. So this is hopefully easy. We know what the series is for sine. Even without our notes, hopefully at this point, we know that sine is the odd powers. So to have the odd powers, I must include x to the first. Oops. The signs alternate, so x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. And they want the first four non-zero terms. So get one more. Okay, now they also want the first four non-zero terms of sine of x squared. So this is just a substitution problem. So this is going to become x squared. This will become x to the sixth over 3 factorial plus x to the 10th over 5 factorial, x to the 14th over 4 factorial. So there we go. First four terms of both series, and they don't want any general term. Great. I'm going to do part B over here. Part B, write the first four non-zero terms for the Taylor series of cosine of x. Okay, this is also one that we're supposed to know. Cosine of x is the even powers, so 1 is included, and then x squared. The powers alternate, and they want the first four non-zero ones. Okay, good. Now, use this and the series for sine of x squared to write the first four non-zero terms of the Taylor series for f. So go back and look at what f was. F was this crazy thing. So they're just setting us up to write the series for sine of x squared plus cosine x. That means I'm supposed to add these two series together. This one plus this one. So I'm going to add this all up. You can write all of these terms and then all of these terms and add up our like terms. So that's basically what we're going to do. I'm going to do this not necessarily in my head, but I'm going to start, the cosine has a 1, and then has a minus x squared over 2 factorial, and this has an x squared. And then we have an x to the fourth over 4 factorial. This has an x to the sixth over 3 factorial. This has an x to the sixth over 6 factorial. Now I only need the first four non-zero terms. So this should probably give me enough when I put my like terms together. So f of x is going to equal 1. Put these two together. So I have a negative 1/2 and a positive 1. So we're going to have a positive x squared over 2. Not factorial, just 2. Plus x to the fourth over 4 factorial. There's no reason I have to reduce that. They're not going to ask me for the general term, so I'm just going to leave it like this. Minus, I got to put these two together. So I'm going to just, for myself, say I have negative 1/6 x to the sixth minus 1 6 factorial is 720. So I've got to add negative 1/6 and negative 720. I mean, I have to put blah, blah, blah. I don't know that this is a it's question number 6, so it's actually not a calculator question. But I don't care. I'm going to use my calculator right now because I feel like it. And I get negative 121. Whoops. Over 720, x to the 6th. So there we go. First 4 non-zero terms of this new Taylor series that got formed by adding up the series for sine of x squared and the series for cosine x. I don't think we've done that together, so now we have. Okay, part C wants find the value of the 6th derivative. So this doesn't help us. This is the 5th derivative. Find the value of the 6th derivative. So what they want me to do here is say, oh, okay, the 6th derivative, this is a Taylor series, even though I created it not from using a Taylor series, I created it in a different way. That's fine. I could have created it with a Taylor series. Well, this is my 6th degree term. So we know that my 6th derivative at 0, pardon me, times x to the 6th over 6 factorial should be the same as whatever this reduced out to, negative 121 over 720 x to the 6th. So this is just to make sure this is clear again. I can write a series in multiple ways. I can write a series by combining two series, and I would get the same thing if I did it out with the Taylor series formula. So this series here, let's say I never went through this process and I just took this and I wrote the series for it by finding all the derivatives and plugging them all into the Taylor series thing. I would get that. If I took that original sine of x squared plus cosine x and I found all the derivatives, and I found all the derivatives at 0, and I plugged them all into the Taylor series format or template, I would get this. So this is a Taylor series, even though it was also made in a different way. So therefore, I can think about this coefficient of the x to the 6th term as being formed as if it were Taylor series. So if I were doing this as a Taylor series, I would have said the 6th derivative of f times x to the 6 over 6 factorial is the same as this 6th degree term. So therefore, 6th derivative of f over 6 factorial is the same as negative 121 over 720. Well, 6 factorial is 720. So that's nice. So therefore, the 6th derivative of f at 0 must be negative 121, which is what they're asking me for. If you're keeping track of scoring, do I have the scoring in front of me? Let's see if I have the rubric here. No, I don't. Oh, yes, I do. So just for scoring purposes, I know we didn't do D yet, but you would have had 3 points for part A, 1 point for the series for sine, 2 points for sine x squared, so those are easy. 3 points for B. So 1 point for the series for cosine and 2 points for getting the series for f of x. For C, you would have gotten 1 point for your value for the 6th derivative. And now we have 2 points remaining for the last part. So this last part is error. And like I said, I don't think I've done a great job at explaining error. So let me first say, what I would be confused about if I were you is how do I know the difference between using literally just the next term? Well, first of all, how do I know they want error? Well, when I see this notation, this tells me they want error. The reason why is they're saying, show that the difference between this piece of 4, that means the polynomial, the 4th degree polynomial. So they're saying, show me that the difference between my polynomial and the actual value is less than 1 over 3,000. Well, that is error. That's saying that the difference between where I'm estimating and where I actually am. So maybe this is my series and then this is my function or whatever. They were really close here, but then once I get to here, they're not so close. What is that error? What is the difference in the y value between the polynomial or the series and the function? So a series and a polynomial can be really used interchangeably, those two words, because the series that I write is a polynomial. It's x squared and x to the fourth and whatever. So that's the first thing that this is really asking you. Show me that the error is less than 1 over 3,000. That's what that said. So they want you to find the error. Well, we have two ways to find it. One way to find error is find literally the next term in an alternating series. Well, that is, usually we have two choices. It says, the problem will say, well, it won't always say, but if we have an alternating series, you can usually just use the next term. If we're not sure, we have to use Lagrange Era Bound. I feel like the problems often will tell us to use the Lagrange Era Bound when we need to use it, but this is an exception. This is a case where we actually do have to use the Lagrange, even though what I have is an alternating series. So I don't have a great way to know the difference. So let's jump into Lagrange almost every time and let's see what happens. I'm not coming up with a great explanation for why I know which one to use. I guess one of the reasons I know which one to use is I never was given a series that like I saw all the terms for. My series had a bunch of x's in it. So when I have a bunch of x's in it, I'm going to have to use the Lagrange Era Bound. If I have a series that is 1/2 or -1/2 plus 1/4 minus 1/8 plus 1/16, then I'm going to use this. I'm just going to pick the next term to represent the error because I have this alternating series that I know the numbers for. So maybe that's a good way to explain it. If I don't have the numbers, I'm going to have to go to Lagrange. So in this case, I don't have the numbers. Everything is x's, so I'm going to have to use Lagrange. It's 2 points, so it's not going to, make or break your score. But if you do know it, it'll really give you a leg up in terms of comparing to other people who take this test, nationwide. So Lagrange Era Bound. All right, so let P sub 4 be the 4th degree polynomial. Find the error. So we have to use the 5th degree term. So we are going to use the 5th degree term. So we are going to use the 5th derivative of f, evaluated at some value c, which we don't even really know, times x minus where we're centered to the 5th over 5 factorial. This is the Lagrange Era Bound. You would get a point just for writing that down, even if the numbers we plug in don't end up being totally correct. Okay, so we know that, this was 0, not a, because we were centered at 0. So what do I plug in for everything? Well, when I plug in my number for x, that's supposed to be where I'm evaluating this thing. Well, look, I'm evaluating the error at 1/4. That's what these are about, because this is like the value of the polynomial at 1/4 minus the value of the function at 1/4. So x is 1/4. Okay, now this is supposed to be the derivative of the function. If they gave me a range of values for x, then I would have to really figure out what would give me the largest number. But now I do know that the 5th derivative at 1/4, let's go up. So this is the graph of the 5th derivative of f. If I go to 1/4, that's here. That graph, right? 1 3/4. See, this is what I find weird. I'm looking at the answers. They tell me that the number 40 should go in for the derivative, the 5th derivative of f. Why 40? Because when I get to 1/4, the biggest number I'm at, oh, no. The number that you plug in for this should be the biggest number that the derivative could be. Well, the biggest number that the derivative could be at 1/4 is not 40, it's like 38. The work for the answer says that I should be plugging in the maximum value for the derivative for x between 0 and 1/4, but still that's not 40. Am I missing something? That's 1. That's 1/2. That's 1/4. Why wouldn't that be like 38? Why do they have that as 40? The maximum of the fifth derivative. I don't know why they're saying 40, other than maybe they're just saying this, I can't really estimate where I'm at, so they're going to choose 40 because it's no bigger than 40. That's really weird, though, and that's really out there. I would plug in like 38, but they're telling me to plug in 40. So we're going to go with it, and we're just going to like give a wish and a prayer. So we're going to say that the maximum this could be is 40, because I can't really tell on this graph where this is. I'm looking to find out what is the y value here when x is 1/4. So I guess they want me to just say, well, I know it can't be bigger than 40. It's definitely less than 40. Whatever. So we're going to say 40. And then this is going to be 1/4 to the 5th over 5 factorial. We want to show that number we have come up with for error is less than 1 over 3,000. So let's compute this. Let's see. So I'm going to have 40 over a 4, a 4, a 4, a 4, a 4, a 5, a 4, a 3, a 2. I'm just seeing if I can reduce this a little bit because this is no calculator. So what would I do if I didn't have a calculator? I would try to at least reduce this a little bit. So 4 goes into 40 10 times, 5 goes into 10 2 times, 2 goes into 2 once. So this reduces to this. I am getting my calculator because I don't care. Not that I don't care, but I don't feel like doing it. So 4 times 4 times 4 times 4 times 4 times 3. Yeah, I get 1 over 3,072, which is less than 1 over 3,000. What a stupid thing to make you have to worry about. So again, that's 2 points. You would have gotten 1 point just for showing you're going to use that Lagrange Era Bound, and then 1 point for getting that answer. Good luck with that.